to another week. And as usual, we'll start by looking at the homework problem. Some of you I've seen the results of that. Well, not the results. I've seen your responses to the form. Some of them were quite childish, but some of you asked for more exercises. But first, you have to do the exercises I give you. So that's an important point I think I want to make. And then you can ask for more exercises. Now, I'll give you more exercises if you ask for them. Just have to come and see. Okay, this is the linear programming problem that you were supposed to solve by the simplex method. So if you have done so, you would have got. Where am I going? I'll make it smaller. What? Okay, maybe I don't have to fit everything at the same time. Okay, you get these three tableaus. We are quiet, please. I don't think there's anything surprising there. So by now you should be able to write the first tableau as a table like this. 5, 2 and 3 become minus 3. The right hand side here, and then coefficients there, and the slack variables. As many slack variables you have constraints, and then pivoting is thing. So in this case, the optimal solution will be that both x1 and x2 are 10. And the objective is therefore 50. And there was one intermediate tableau where x2 was 15 and x1 was 0. X1 and basis 0. And that's simple enough. And the question asked you to plot the feasible region of this LP, so all the feasible solutions in the plane. And the way this looks is this. Okay. So if you look at the tableau, which I'm going to put here, you see that in the first tableau, both x1 and x2 are 0. So the point where x1 and x2 are both 0 is this one with both coordinates 0 in the bottom left corner. And then in the second solution, this one, x2 is 15. So x2 is the vertical axis, and x1 is the horizontal axis. And where x2 is 15 and x1 is 0, we get the points with coordinates 0 and 15, and this point in that corner over there. And then the final solution is where both x1 and x2 are 10, and that's this point C. Well, there's a little c there. So what happens in the pivoting is, as we showed last week, is that the pivot step moves from one corner point of the feasible region, which in this case is a polygon, but it can be in a higher dimension. Of course, you get something that's called a polytope. So if you had 3 decision variables, you'd have a 3-dimensional object, and if you have more than 3 decision variables, then you have a highly dimensional object. But it still looks like a, well, nobody knows what it looks like, but you can still imagine it as a 3-dimensional thing. So you're going from one corner to another, and then in the second step you're going to this point there, and that's the optimal solution. Okay, that's about it, I think. Any questions? No? That's probably clear. So you can, if you've done the simplex, you get 1 mark, and if you've done the picture, you get 1 mark, and so that altogether you can get at most 2, and you can mark it here. And get it. Thank you. If you've done nothing, then just sign in. Right. That's the homework. Oh, and can I please? Okay. Okay. The plan for today is to look at problems like this. No. Look at the problems like this. We've covered all the standard problems, like I said. We also know how to do minimization problems. We did that last week. What is funny then about this example that we don't know how to do? Or some of you maybe do know how to do, but we haven't covered yet. Anybody spot anything strange? Agree on who's going to tell me. Okay.
The slack variables have to be negative.
The slack variables have to be negative. Oh. So that's greater than or equal in the constraint, like here. So that one doesn't matter. There and there. Yes, that's exactly what we don't know how to do. So when we're doing the simplex, what we're normally we introduce slack variables. But here we can't really introduce the slack variables in the same way as we usually do, because so we would normally do, which we won't do in this case, x1 plus x2 plus x3 equals plus s1. What I mean, yeah, plus s1 equals 4. Done enough of the handouts at the back? Okay. Oh, you don't know yet. It's not got there yet. So that's what we would normally do. But then we would have to add the condition that S1 is less than or equal to 0. Because if you want x1 plus x2 plus x3 to be greater than 4, then you have to add something negative to it to get 4. But that's not good. Because the simplex method needs all the variables to be positive or 0. So we don't want to do that. Okay, so we could do what Matt was suggesting. I think, and we subtract S1 to get 4, and we can do the same thing with the second constraint. And there's no problem with the objective. now we have x1, x2, x3, s1, s2 non-negative, and oops, and we like that. Or do we? Has everybody got the handout? One missing, a couple missing. Okay. Put them down there. Now I have to say something about them. Okay, now while you're thinking why it's not good, I have to apologize because I printed 75 or what of these, and then I noticed that I've put maximize in onto the handout, while actually what I want to do is minimize. So please, if you could change this to minimize. Doesn't have any influence on what we're doing now, because now we're in trouble. And the reason I put not good there, and the reason we're in trouble, is that the simplex method wants some basic variables. And what do the columns of the basic variables have to satisfy? They have to have a 1 and 0 in the rest of the column. But here we have a -1 and zeros. So that's not good, because we need basic variables with 1 and zeros in that column. Okay, so what could we do? Well, we could multiply the first two equations by -1. And then we have, the first one would be -x1 minus x2 minus x3 plus s1 equals -4. Okay, we could do that. Now we have a 1 for a basic variable, but what's the problem now? Any problem? Now the problem is that in what we would like to be the basic feasible solution, when we set all the x's to 0, s1 would be -4. But we want s1 to be greater than or equal to 0. So we wouldn't get a basic feasible solution. And that's not good. So the basic solution is not feasible. It would be s1 equals -4, s2 equals -5. However, there is a way out. One way out is that we don't mind for a moment that we have negative values in the right-hand side and do something about it, and that's the way we learn in the second year of our module, if you decide to take it. But now we're going to do a different method, how to get rid of these. And that is called the two-stage simplex method. So the two-stage simplex method does the following. Well, because it's called two-stage, well, not because, it's called two-stage for a reason, and it's called two-stage because it has two stages. So in the first stage, it finds a basic feasible solution of this problem, and in the second stage, it then solves the minimization problem that we have to do. Okay? And the way, so the first stage where we need to find a feasible solution does it by looking at these and adding variables that are called artificial variables. Okay, so what we do is the first constraint, there is no basic variable, so we add a basic variable to have one. There's nothing with a basis because there's nothing with a coefficient 1 that wouldn't appear in any other constraint. So we add it, and we'll call it A1. And I'll call it an artificial variable. And in the second constraint, we add another artificial variable, and then we still have this z minus 6x1 minus 7x2 minus 4x3 equals 0. And we still have that x1, x2, x3, s1, s2, a1, a2. We want all of these variables being on negative. Oh, it's hidden. And I've left an empty line there because we still haven't got an objective for this first stage. So now the question is, if I find x1, x2, x3, s1, s2, a1, and a2 that satisfy these equations, okay, and then I forget the a1 and a2, and I plug in all the x's into these constraints, are they going to be satisfied? Yes or no? So again, I find values that satisfy these equations down here, and I put them there, and I forget the a1 and a2. Are these equations going to be satisfied as well? Too simple a question. No. No. You think no? Anybody think? Anybody else think that they're not going to be satisfied? So who thinks they are going to be satisfied? Go on. Sometimes they are. When exactly can I take all these x's and s's that for which these equations hold, and put them there and get valid equations. When can I do that? Oh, yes. When both A1 and A2 are 0, then I can do it. If A1 and A2 are both 0, then I can take these values and put them there, and I'll get this equation. So what I want to do here, I want to find a solution. Where do I put it? Okay, here. We want a solution in which both A1 and A2 are equal to 0. Okay? Now, A1 and A2 can't be negative. So if I know that A1 plus A2 is 0, that can't happen unless both A1 and A2 are 0. Because they can't be negative. You have two numbers, none of them is negative, you add them, you get a 0. It must be that they were both 0. And so the question is, can I find some values for these x's and s's in such a way that I would get both A1 and A2, so sum A1 and plus A2 to be 0, and if I want the answer to this question, I can ask linear programming, can't I? Because I can say, what can I say? If we minimize A1 and A2 subject to these constraints, if we get 0, then we'll get a solution in which both A1 and A2 are 0. And we're happy, and we found a basic feasible solution for our original problem. But if the minimum is larger than 0, then we know that it's not possible to find x's and s's for which A1 and A2 are both 0, and then we know that we can't ever satisfy these constraints up there with non-negative numbers. Okay, so that's the key, and that's what's called the first stage, in which we want to find a basic feasible solution for the original problem. And it goes like this: it adds two artificial variables. It minimizes the sum of all the artificial variables, and if that sum is minimized to 0, we found a feasible solution, and if not, then we can't find it possibly. Okay, so for some reason I call this objective G, so I'll just put G minus A1 minus A2 equals 0, because G is A1 plus A2. So that's the objective of the first stage procedure. Okay, but now this is not good. Why is this not good? I've destroyed it again. This is not good because I want A1 and A2 to form the initial basis. And if they form the initial basis, they should have 1 zeros in the rest. They should have 1 zeros in the rest. But that's easy to fix because we can do a simple row reduction by adding first and the second equation to the last, and these will vanish, and then we get the G's. So I'll mark them now. So this is A, this is B, this is Z, this is G. So now I want the new G to be the old G plus A plus B, because I want to get rid of the two minus A's. So what I get is G plus 2x1 plus 3x2 plus 5x3 minus S1 minus S2 equals 9. Do you agree? Okay. Thank you. Okay, now the rest is easy. Got this. So I can just, okay, I'm not doing it very well, right? Because I'm covering this already. So what are the variables here? We have x1, x2, x3, s1, s2, a1, a2. The initial basis is a1, a2. We have a z and we have a g. The values are 4, 5, 0, and 9. Well, you can't see it, but I can. And I'm just going to put all the coefficients there. 1, 1, 1, minus 1, 0, 1, 0, I think. Well, you can do it yourselves, because you know enough. Okay, everybody with me now? So, what are we doing? We're minimizing G, which means we're trying to do what? Pivot? In which way? In what way, really? What's the pivot step? What is this optimal? I can't hear you. Is the table optimal? No. Why not? Negative values in the Z equation. Does that matter? No, because remember, we're minimizing, so what we mind is positive value in there. Well, actually, the G low now. Yeah, now we're minimizing G in the first stage. So when we're minimizing G in the first stage, what we're trying to achieve is no positive entries in the G low. Okay? So we have positive entries. We have, well, the rule of Danzig would tell you to look at the positive, the largest among them. So that's the 5. And then the ratio test is the same. So what are the ratios? 4 divided by 1 and 5 divided by 4. And we don't divide by anything. Well, we don't actually want to take z out of the basis. That would be a bad thing to do. So we only look at the first 2. And this means that this element over here is going to be the pivot element. Have you finished the pivot step yet? Well, now you know what to do, so do it. You have 2 minutes. Well, 3. I'll be doing it myself, but don't mind me. I'll probably get it wrong. But you have a chance to remind yourself about how to do a pivot step. That was easy. Have you got it? Maybe. I told you not to watch what I'm doing. You're supposed to be doing it on your own. So who knows what to do in a pivot step? Who doesn't know? Everybody knows. Oh, so finish it. Okay. Do it by taking multiple of the extremes, adding it to subtracting it from do anything else. And we lose the property in the basic value. Now, A1 next to one, and 0 and 1, so next 3 and 0. So the way you get this is so in my case, the Z flow is quite simple because where I am so think of them as matrix, which is the second row is the third. That's how I got the top row I've got from taking the original construct and took away the new six. That's it. From 1. Okay. This doesn't work. I'm not sure why, but people don't know how to do it. All right, so how does pivoting work? Do I have to say it again? Well, the main purpose is to get the zeros and ones in the basic columns. So here what I'm doing is the new second row. The new second row is the old second row divided by 4. Okay. The new first row is the new first row take away, sorry, the old first row take away the new second row, because like this, I'm achieving the 0 there without destroying this 1 over here. The new third row is the old third row plus 4 times the new second row, because like this, I'm getting a 0 there from the -4 and not destroying anything anywhere else. And the new fourth row is the original fourth row. I think I have to take away 5 times the new row 2. And if you do it, you get 3/4, 1/2, 0, -1, 1/4, 0, -5/4. Is that correct? Can anybody spot? That's 2. Oh, I forgot to put the labels there, sorry. Then again, S2 column is not good. 1/2. Yeah, thank you. It says 1/4 in my notes, so I suppose you're right. I was doing it. I was doing it in my notes. Okay.
Yeah. No, in the Z on the top one. Should a -4 be a -12?
A -4 should be a -12.
It's +12 x3 in the actual.
Are you joking? Oh, this is going to completely destroy everything. No, it's not going to completely destroy. Okay. Why is there a -4? Why has nobody noticed before? Okay, apologies. You see, I'm making these things as we go. Yeah, so this is indeed -12, which means that we should also put the -12 here, right? But what does it do to this tableau is now this 4 needs to be 12. And this is all wrong. Okay, so what you're supposed to have is 15 -3. Is anybody checking this? Because probably going to be -1. -3 and 3. Okay. Okay, any more objections? Okay, have we finished this then? Finished the minimization or not? No? There's still positive values in the G. So which element shall we take as the pivot element now? Okay. The largest one is 3/4. The ratios are 11/3 and 5. 11/3 is less than 5, I think. So this is going to be the pivot element. Now I will spare you. Okay, so now this has become x1, x3, zg. The first row is divided by 3/4, so you should be getting 11/3, 1, 2/3, 0, -4/3, 1/3, 1/3, -1/3, and it's x1, x2, x3, s1, s2, a1, a2. Just quickly finish this. 1/3, 0, 1/3, 1, 1/3, -1/3, and -1/3, 1/3. Okay. And z is 26, 0, 1, 0, -4, -4, -2, 2. And g is 0 all the way here. Okay, did you get the same? Excellent. So now what? Finished? Okay, so what's the optimal solution of the first stage? Minimized G, we get G is 0. And G is 0 is good because that means, as we discussed before, that we get a feasible solution of our original problem. So what happens now? We know yes. Is S2 for the Z naught minus 2. Is it? It's not in my table here. So if it is, then I don't know. It's possible. I'll check it. Which one? This one. I'll check it later. We're running out of time, so I want to finish this quickly. So now, what you do in this situation is not pack, but look here. And now what I said was we can throw out the A's, A1 and A2. And the way we throw them out, for example, is that we just throw them out. So this goes away. And we have a tableau in which we try to minimize. Oh, that's the problem. Minimize that. So now look, you see the tableau is now smaller. But it's is it optimal? No. Why not? Yeah, so there is a 1 here, which is saying that the Z has not been minimized yet. So if you want to minimize Z, you look at the 1. What are the ratios? 11/2 and 1. So that means that this 1/3 is going to be the pivot element, and you need to finish it. Finish for next week. Any more objections? Where's everybody going? You don't have to go yet. Black Friday shopping is over now, so there's no rush. Okay, thanks for coming. See you next time.